Similar to beams and frames, the force method can be a very efficient analysis tool for indeterminate trusses if there are only 1 or 2 degrees indeterminate. So in this problem we'll analyze an indeterminate truss and we'll use the force method. The key concepts we'll use are calculating the degree of indeterminacy, selecting a redundant for the force method of analysis, and predicting deflection of a truss using virtual work. And here is our truss. It has 3 legs, each supported on one end, and we're to find the force in each member of the truss. The product of cross-sectional area and modulus elasticity, AE, is going to be the same for each of the 3 pieces. And here's our approach. We'll want to start by generating an approximate answer. Because after forming lengthy calculations to apply the force method, we're going to want to have some way of establishing whether we have a reasonable result. And so we'll use our approximate answer to compare against. And we'll begin the force method by calculating the degree of indeterminacy so that we can figure out how many redundants we need, choose them, and write our equations of compatibility. We'll then need to predict deflection of the truss. In this case, we'll call it the primary structure, and so it'll be a truss that is determinate. We will release the redundant, or redundants, due to the applied load, which is 500 pounds in this case. Then we'll also need to calculate deflection of the primary structure or released structure. Due to a unit redundant. We'll then be ready to find the redundant or redundants. With that information, we'll be able to use just equilibrium to find the remaining member forces. Then we'll wrap up by comparing with the approximation and evaluating the reasonableness of our results. Step 1. Let's approximate the answer. And here's the assumption we're going to make. This lateral force that we've applied, we're going to say will be carried equally in the diagonal members. This is an assumption we talked about in a previous chapter. If I draw free body of joint B, what this means is that the 500 pounds applied load will be carried in member BD and member AB in its horizontal components. So the horizontal component of force BD will be 500 divided by 2, or 250 pounds. And the horizontal component in AB will be 500 divided by 2, or 250 pounds. Now remember, there's also member BC, but it's vertical, so it has no horizontal component. If we take a look at our geometry over here, we have a 3, 4, 5 triangle, and on this side a 3, 4, 5 triangle, which means that 3/5 of force AB is a minus 250 pounds, and so the force in member AB is a negative 417 pounds, or it's 417 pounds in compression. Over on this side, 3/5 of force in member BD will be 250 pounds, and so the force in member BD will predict to be 417 pounds in tension. Now, let's apply vertical equilibrium to our free body. We have the sum of the forces in the y direction. We'll take up as positive, which means we have that is our x and that is our y. We have a negative 4/5 vertical component of the force in member AB, which we said is already a negative 417 pounds. We have a negative contribution from member BC, and a negative 4/5 of the force in member BD, which we said was a positive 417 pounds. When all of those are combined, we predict the force in member BC to be 0. So we'll come back to these predictions at the end in order to evaluate the reasonableness of our force method results. Step 2. After we figure out how many degrees in determinant, we'll be able to figure out how many redundants we need, select those, and write our equations of compatibility. So indeterminacy. We have unknown reactions at A, C, and D. So there are 6 unknown reactions. We have 1, 2, 3 bar forces or member forces, and we subtract 2 equations of equilibrium times each node or joint. 1, 2, 3, 4. And we get 1 degree indeterminate, which means we need to choose 1 redundant. And I can choose any redundant, any internal force or reaction, as long as the remaining structure, the primary structure, is determinate and stable. In this case, I will choose the axial force in member BD to be my redundant, which means my structure basically looks like that. We'll cut it, and it has the applied load, and this will open up an amount delta BD, and we'll superimpose the axial force in BD times a situation where we have a unit force acting on the ends of this cut, and it will cause an overlap. We'll call the flexibility coefficient BD, comma, BD. So our equation of compatibility becomes the gap at BD plus the force in member BD times the flexibility coefficient have to add up to 0. Now we're ready to begin step 3. We're going to predict deflection of the primary structure which is the determinate structure without the redundant, due to the applied load. The 500 pounds lateral force in this case. To predict that deflection, we're going to need to use virtual work since it's a truss. Let's start by finding the normal forces in the truss due to the real load. Now remember, this is not of the indeterminate truss, but of the primary structure, which is cut in between B and D. And if we cut that member, the normal force in member BD, due to the 500 pounds lateral load, is going to be 0. So let's use method of joints, and let's draw a free body diagram of joint B. We have the applied load, 500 pounds. We have our unknown normal force in member BC, and our unknown normal force in member AB. We saw before that this is a 3, 4, 5 geometry for member AB. I'm going to label my axis in this case Y being down and X to the left. Let's apply equilibrium. Some forces in the X direction. So to the left will be positive. That gives me a positive 3/5 contribution from the normal force in AB and a positive contribution from the applied load of 500 pounds. I solve that. The normal force in member AB is a negative 833 pounds, which means it's 833 pounds in compression. Now, let's sum forces in the y direction. We have, according to our coordinate system, down is positive. We get a positive 4/5 contribution from member AB, which we have found to be a negative 833 pounds. And we get a positive contribution from member BC. If I solve for the force in member BC, I get a positive 667 pounds. So it is in tension. Now the normal forces due to the virtual load. So we don't have the applied 500 pounds, and remember this is of the primary structure, so this structure is cut at BD, and so we have this piece with a virtual force on it, and this piece with the other part of the virtual force applied. So the virtual normal force in member BD is a positive 1. Now let's go back and apply method of joints, and we'll look at joint B. Again, I'll take to the left as a positive X and down as a positive Y. I already know that the force in member BD is 1. We have an unknown normal force in member AB and an unknown normal force in member BC, and we know the geometry of the problem is 3, 4, 5 for the two diagonal members. So let's sum forces in the x direction first, and by our coordinate system we'll take to the left as positive, which means we have a positive 3/5 contribution from the normal in member AB. We have a negative 3/5 contribution from the normal in BD, which is a positive 1. So the normal in member AB is a positive 1. Now vertical equilibrium. Sum of the forces of the y equals 0. According to our coordinate system, down is positive. We get a positive 4/5 contribution from member AB, which is a positive 1. A positive contribution from member BC, and a positive 4/5 contribution from member BD, which is a positive 1 also. We'll combine those and find that the axial force or normal force in member BC is a negative 1.6. We're now ready to calculate the gap created in member BD. The virtual work formula is the summation of the virtual normal force times the real normal force, the length of the member, over AE for the member. And in this case, we have a virtual force of +1, our normal force in member AB we found to be negative 833 pounds, member AB is 5 feet long. We divide that by AE. We add to it the normal force due to the virtual load, so negative 1.6 times the normal force due to the real load, which we found to be a positive 667 pounds. That member is 4 feet tall over AE. And we add in the contribution from member BC, and the virtual normal force is a positive 1. Due to the real load, we found it to be 0. And even though that whole term will then become 0, I'll finish writing it out for completeness. When I combine all of these, we find that the deflection, or the separation at BD at its cut, is a negative 4165 foot-pounds over AE minus 4269 foot-pounds over AE. Put those together, we get a negative 8430 foot-pounds over AE. And remember, we drew our virtual force pulling on the ends so that a positive delta would mean overlap. Okay, so negative means there's a gap, which is what we expected. Good. Now step 4. To predict deflection of the primary structure, again, that means it's cut in member BD, this time due to a unit redundant. So we're not dealing with the 500 pounds lateral load, we're only dealing with, at the cut, a unit redundant, which looks exactly like the virtual system. So to calculate our flexibility coefficient, or our overlap, FBD, BD, we need only sum the virtual axial forces or virtual normal forces squared times the length of each member over AE. And in the case of the structure is drawn to our right, for member AB we had found that the normal force due to the virtual load was a +1. We'll square that. It's 5 feet long over AE. Member BC had a -1.6 normal force. We'll square that times 4 feet over AE. And then member BC was a +1. We'll square that, 5 feet long over AE. Put those together and we get a positive 20.2 feet over AE. So when the redundant pulls in tension, we get an overlap instead of a gap. Now we're ready for step 5, which is to find the redundant. Our equation of compatibility we had written as the gap in member BD plus the unknown force in member BD times the flexibility coefficient equals 0. But we just calculated that the gap in BD is a -8,430 foot-pounds over AE. To which we add our unknown force in member BD times our flexibility coefficient, 20.2 feet over AE. Those have to add up to 0. Solve that for my unknown force in member BD and get a positive 417 pounds. So it is in tension. Now step 6. We'll apply equations of equilibrium to find the remaining member forces. So let's go to joint B and we'll apply method of joints there. We have our applied load of 500 pounds. We now know that member BD is 417 pounds in tension. So we have our unknown force in member BC and our unknown force in member AB. But we know our geometry here is such that this is a 3, 4, 5 and this is a 3, 4, 5, describing the angle or slope of those members. We'll take down as the y-axis, to the left as the x-axis, and let some forces in the x direction first by this coordinate system. To the left will be positive, and so we'll take 3/5 of the force in member AB, and that's a positive contribution. We have a full 500 pounds positive contribution from the applied lateral load. We have a -3/5 of the 417 pounds, which is the force in member BD. That's one equation, one unknown. We'll solve it for the force in member AB and find it's a negative 417 pounds. So member AB is in compression. Now go to vertical equilibrium, sum of forces in the y direction. Based on this coordinate system, down will be positive. We'll have a positive 4/5 contribution from force in member AB, but that's a negative 417 pounds. We'll have a positive contribution from the force in member BC, and we'll have a positive 4/5 contribution from the force in member BD, which is a positive 417 pounds. Put those together, and the force in BC we get to be 0. So based on the force method, we predict a positive 417 pounds in BD, 0 in BC, and a negative 417 pounds in member AB. So now we're ready for step 7. We'll compare with the approximation. We just concluded that from the force method, we get a positive 417 pounds, a negative 417 pounds, and a 0 for the three members. If we go back and look at the results from our approximate analysis, we get a negative 417 pounds, a positive 417 pounds, and a 0. So our answers match exactly. Let's think about that for a moment. They match exactly because the quantity AE over L is the same for both diagonal members. Otherwise, there would have been a difference. Now, why the quantity AE over L? Well, we'll get to that when we start talking about the stiffness method of analysis. Now let's go back and review the process we used to obtain our answers. We began by performing approximate analysis of the truss, and to do that we assume that the lateral force is carried equally in the diagonal members, and so we found that the force in member AB was the same magnitude as the force in member BD, but opposite signs, and we predicted that the force in member BC would be 0 based on this approximate analysis. In order to start the force method, we needed to figure out how many degrees indeterminate this truss is. We found it's 1 degree indeterminate. We could have chosen any of the member forces to be the redundant. I happened to choose member BD, and we wrote our equation of compatibility. Since we're dealing with deflections of a truss, we needed to use virtual work. So first we calculated the normal forces of the primary structure, that is the structure where member BD is cut, and these normal forces were due to the real load of 500 pounds applied at joint B. We then took off the real load and applied a unit virtual force at the cut in member BD, calculated the internal forces or normal forces due to that virtual load, and with that we were able to calculate how much of an overlap or gap there would be in member BD due to the real force applied when member BD is cut. And the negative we found in our answer means that it's actually a gap, which we expected. We then found the deflection of that primary structure due to a unit redundant, which looks exactly the same as when our virtual load is applied. So we calculated that, found it to be positive, which means that when the unit redundant is applied in tension, we get an overlap at the cut in member BD. We combined that information and found the redundant. We then applied equilibrium using method of joints at joint B. In order to find the other two member forces, we summarized those on the sketch of the truss, compared them with our approximation, and in this case they matched exactly. So we're reasonably sure that we have a reliable prediction of what the internal forces would be due for this indeterminate truss due to the lateral load of 500 pounds. Great job!